Hello, welcome to the next in our webinar series. Just a few announcements to start with. There was a slight mix-up on the email that went out today, so just in case you haven't seen it, the email and the calendar were out of date. We are starting off with Greg's presentation today. Tomorrow is going to be the two Erics on stretching time and space, first things. We are now also up to date with all of our video recordings, so if you want to go back through any of the presentations, you simply go to the Astrobiology Future website and select any of the events, and the associated YouTube video will be linked in there. The slides for this event are also on each of the event entries. So if you connect to this and you're only listening to the audio, you can download the slides directly from the website. And finally, the meeting is being recorded. So at this point, let me pass over to Greg. Take it away.
Thanks, Andy. So my name is Greg Springsteen. I was one of the participants in the Astrobiology Roadmap meeting. And what I'm going to be talking about today is the synthesis and assembly of populations of stable oligomers. Now, the text that we plan, or at least that is currently in the paper, will be highlighted in red. And I think this document will be opened quite soon, maybe right after the presentation. Okay. So first, our justifications for this topic. Why are we interested in this as part of the Astrobiology Roadmap? And so our group came up with three primary justifications. One, polymers are uniquely capable of selective catalytic and genetic functions necessary to life. So we've got the large size of a polymer incorporating a transition state in a polydentate fashion, giving some selectivity to the catalysis. Also, these polymers, or linear polymers, we can generate libraries with quite a bit of structural variability with an extraordinarily limited set of reaction types. For example, we could just do the addition of the monomer if we have multiple monomers to generate all sorts of structural variability in an environment of which just that monomer coupling is the only available synthetic reaction type. Additionally, chemical and phylogenetic evidence suggests that both extant and ancestral metabolisms, as far as we are aware at the moment, are dependent on polymers for structural, catalytic, and genetic functions. It makes a lot of sense to go after an understanding of how polymers or oligomers were generated prebiotically. So as a broad overview of the topic explanation, in most plausible prebiotic hypotheses, abiotic monomers, and we're keeping that very broad, amino acids, nucleotides, monosaccharides, were condensed by abiotic dehydration condensation reactions to form oligomers. Life evolved from within this milieu of reversible polymerization, is a plausible prebiotic hypothesis. However, condensation reactions are thermodynamically problematic in aqueous media, of course, because we are generating water in these condensation reactions. Additionally, carboxylate and phosphate esterification/amidation reactions suffer from large kinetic barriers in near-neutral aqueous environments, primarily because of the poor leaving groups under neutral conditions from these carboxylic acids and these phosphate acids as well. So, mechanisms by which dehydration and condensation reactions may have been thermodynamically driven and or kinetically facilitated include incorporation of high potential energy activating groups, 2, polymer growth in non-aqueous or dry down environments, or potentially 3, non-covalent pre-assembly of monomers either with or without a template, that template being broadly defined, and 4, some polymer properties that inhibit degradation of the polymers of the larger complex selectively of one complex over other complexes. And so we've broken up each of these topics into a number of sub-questions. And so to hit these really one by one. So the first, we talked about it on the previous slide, is chemical activation. So what's polymerization driven, and here I'm just going to broadly speak of thermodynamically or kinetically, by chemical coupling agents. And then what is the source and persistence of these agents? And that is often a particularly problematic question. Now, it's not hard to envision what these agents might have been. We look at carbodiimide, right? Carbodiimide chemistry is very well known for coupling chemistry. Diaminomalonitrile, it not only leads to nucleobases, but is a reasonable dehydrating reagent. Hydrogen cyanide is a dehydrating reagent. Also, the phosphates, trimetaphosphate, is a dehydrating reagent. So we can imagine all of these catalyzing the coupling of monomers. They are in themselves just dehydrated reagents. So in that sense, we're just pushing the question back to what was the source of the dehydration to generate these monomers, these agents, and why were they not hydrolyzed in their environments? Question 2, what is the role of phosphate in early dehydration polymerization? I think this is a reasonable separate question from the first one, in that extant biology is driven by triphosphate catalysis in terms of dehydration. And so what was the origin of that phosphate-driven dehydration? And if it wasn't the first dehydrating reagents, what were the mechanisms to move from a, say, carbodiimide-based dehydration environment to a nucleotide triphosphate-driven environment? Additionally, or let's say alternatively, if we don't have these high potential energy dehydrating reactions, were we potentially doing these condensation polymerizations in alternative solvents or environments? So what are potential non-aqueous environments? We can think of things like formamide, which we've seen in the literature, hydrocarbons, deep eutectic environments, potentially in the membranes of micelles. If oligomerization reactions occurred within these solvent/environments, this dehydration step may have been thermodynamically favorable and kinetically feasible, one or the other or both. So investigation of alternative solvent systems with respect to accumulation in geochemical and cosmological contexts may justify these environments as prebiotically plausible. And additionally, was polymerization driven by water activity cycling? So are we talking about conditions that are dry, whether we're talking about dry down conditions or just our solvents becoming dry in cycling conditions, whether temperature, day, night, tidal, and on. So below we just have just some structures to exemplify kind of the things that we're thinking of, the common urea-based deep eutectics, the formamide, ammonium formate, non-aqueous liquids, and the hydrocarbons down below. All right, a third question. What about polymer sustainability? So were these early polymers that gave rise to biopolymers thermodynamically advantaged or kinetically trapped? What polymer properties could potentially confer resistance to hydrolysis or other degradation leading to a kinetic trapping? And what roles do polymer solubility, solvation, and hydrophobicity play in the evolution of functional polymers? So we imagine that polymer folding, polymer solubility are going to be important questions in our understanding of how these first oligomers/polymers arose and evolved function. All right, next, pre-assembly of monomers. So if we look at biopolymers, right, there's a strong sense of non-covalent interactions, whether we're looking at the beta sheets of peptides, which I got in the upper left, or we're looking at the hydrogen bonding patterns of nucleic acids, which I got in the top right. There's this non-covalent association. So one could ask, did this non-covalent association precede the covalent polymerization? And so that's the first question we have down below. So was this polymerization dynamic or templated before that the covalent bonds formed? We can also ask what other mechanisms promote high effective concentrations of monomers preceding covalent bond formation: thermal convection, surface absorption, permeability, lots of other potential ideas. And if we are imagining scenarios at which these monomers were laid down non-covalently before non-covalent bond formation, can we imagine scenarios in which this homochirality arose not because of a preference of monomers, but because of a preference of how these monomers interacted in their local environment? A big part of this question is also what can we infer from extant biopolymers, since our extant biology is so polymer-based. So what does the mechanisms of polymerization in extant biology, so besides lipids, primarily dehydrative polymerization, tell us about the early biotic environment, as far as the early biotic environment being potentially dehydrative? Are irregular or branched polymers plausible precursors to functional biopolymers? So we see primarily linear polymers now, besides some notable exceptions with the disulfide bonds, for example. But in a prebiotic sense, it's very hard to limit polymers to just linear. Right there, if we look at peptides, for example, or the 2', 3' ribose, right, there are lots of opportunities to branch out in our pre-biopolymeric systems. And when did the primacy of polyphosphate-driven condensation arise? And if it wasn't the first, what were the mechanisms of transferring that dehydrative potential from earlier precursors? And then our last slide is connections to other roadmap topics, and there are a lot. Right? What is our library of potential monomers, and what was the synthesis of these monomers? That might give us some clues as to what the environment was that led to the dehydration of these monomers once generated. What are the common attributes of extant living systems, and what can they tell us about all living systems? So what was the driver? Was there a redox driver, for example, of these dehydrative conditions? How did macromolecules gain function? So of course, how do we link the folding of macromolecules into some functional catalyst genetic polymer? What does that tell us about the environment at which the covalent bond formation of those macromolecules happened? What environmental factors are coupled to the emergence of life? So there's got to be a non-equilibrium driving here, particularly if we're leading to aqueous conditions. Again, it brings us back to redox and dehydrative conditions. So what environment were we in? Laboratory models of earliest cellular life. Again, if we are imagining that we are arising in aqueous conditions, how do we justify that in terms of the thermodynamics and the kinetics of this polymerization? And how did polypeptide meet polynucleotide? There's anything that we learn about the polymerization of one system, our polypeptide system, is likely going to play a large role in our understanding of the condensation polymerization in the other system. So there's going to be a lot of crosstalk between these two worlds, at least the study of these two systems, once we understand in one or the other how this dehydrative condensation polymerization may have arisen. So I would happily take any questions, and you can certainly look at the roadmap document, and I would love to see anybody's suggestions on that document as well of how we're going to potentially take this paper forward. Thanks for your time and attention, and I look forward to hearing from you.
Okay, so we have a select group that appears in the participant list here. I'm not sure if we have other people who are also dialed in. Just to say to our participants who arrived partway through, obviously this is being recorded, so you can run back and see the beginning of it as well. But let me just throw it open because our audio lines are now open. Lee or Alyssa, or even Lindsay, because you're there. Do you have any questions or observations that you want to make now? And actually, just before you do that, let me just respond to Greg's point. The document is currently in read-only mode, but in a few minutes it will be flipped over so that you'll be able to add comments to it. So by all means, add your thoughts directly in the document as well. But coming back to our participants, are there any questions or observations that you'd like to make at this point?
Hello, this is Melissa. No comments from me, but thank you, Greg.
Thanks, Melissa.
Hey, this is Lindsay. Can you all hear me?
Hey, Lindsay.
Yes, we can.
Great. I apologize that I came in a bit late, but I would sort of like to direct the same question to you that I directed to the last group, which was, if we're looking at things that we can think about working on in the next 10 years, et cetera. I mean, that's sort of the general concept of this whole program, this whole astrobiology strategy. But is there anything specific that you would want to point to about that? Specific questions, in a less general sense, in a more directed sense, that you think we're gonna get to.
You said not general, and then I'm going to answer generally, but the idea of drivers of non-equilibrium environments and how they were coupled to polymer synthesis, I think is very fascinating. And I think whether the answer comes directly from this question or from others that we pertain to here, there's a tremendous amount of crosstalk, right? If we're talking about a redox driver, for example, of polymerization, as we see now, it's quite complicated in extant biology how we couple redox energy to ATP synthesis and then to this dehydrate of polymerization. And so which way did that occur prebiotically? Was it dehydration first or redox coupling first? So I think what is fascinating about this concept is we are either going to teach or learn from a great deal of other questions.
Okay. Any other observations?
Does that answer, Lindsay, your question specifically enough?
We'll go with that, sure.
Okay. I'm very interested specifically in realistic coupling reagents. Right? We see a lot of those in the literature. Can we imagine environments at which they persist and are effective generators of polymers? And I would like to see that explored in the very near term.
Great. Any other thoughts, questions that people want to pose at this point? Okay. We will go and flip the switch on your document. Greg, thank you very much for doing this. Appreciate that. And if I can encourage everyone, whether you are live now or catching this and at the recording, please go and put your thoughts and comments directly in the document. The document's linked straight from the front page of the site, and it will help the team enormously if you can just add anything to help them strengthen the paper. That would be wonderful. Thank you very much.
Okay. Document. Thanks.
Cheers.
Thanks, Greg.